Okay, it's Brian, and this week we're going to start talking about circuits. And the first two concepts we're going to consider is current and resistance, and that is the material of chapter 22. But that naturally leads us into the material of chapter 23, which is more complex circuits. And we will get to those by the end of the first week of talking about circuits, and so the end of this set of slides. And the basic definitions we have to worry about are current, and current is the flow of charge, and then resistance. And resistance, well, I'll come back to it. It'll be easier just to kind of like show you what it is. And then we're going to come up with some rules for circuits that we can use to simplify complicated circuits and treat them simply. Now let's take a look at the basics of chapter 22. And they're basically summed up on this little rectangle here, which is in the chapter summary of chapter 22. We're going to define current as the motion of positive charges. And it doesn't really matter if they're positives or negatives that are moving. We can model it as the motion of positive charges, and it will allow us to completely specify everything that's happening in circuits. And we define current this way. Current is just equal to delta Q over delta T. So imagine sitting at one point in a circuit and seeing how many charges pass us by. That's the current, and it's delta Q over delta T. The units of current are, of course, going to be coulombs per second. 1 coulomb per second is defined as 1 amp, or if I use the abbreviation for it, 1A. Now the basic circuit we're going to consider in the chapter is outlined in some detail in this little box. You have a source of EMF, which is basically a potential difference, but a potential difference that has energy. And so charges get raised to a higher potential. They get raised to a higher potential energy. There's an energy source to make that happen. And our first EMF we're going to look at is a battery. And inside a battery, we model it as being this charge escalator, where it just raises the charges to a higher potential, and therefore a higher potential energy. And then they subsequently roll downhill through an external circuit, end up at the negative terminal, and get brought back up. And in this circuit, we're including a resistor. And inside a resistor, as the charges are moving through the resistor, they have collisions. And as a consequence, they lose energy in those collisions, and they lose energy to thermal energy. So I've put in a certain amount of potential energy in the battery. And then when the charges go downhill, they lose that energy to thermal energy. And so there's a change in thermal energy. And so potential energy of the charges is increasing. And as the charges decrease their potential energy, they give it to thermal energy of the resistor that they're flowing through. That's basically what a resistor is, okay? And that's our basic circuit. So it relates to the change in potential that we've seen before, the change in potential energy that we've seen before. One new definition of current that looks like this. But there's a few more definitions. In a resistor, okay, if I put a potential difference across it, okay, and the resistance has a resistance of R, and R is our basic unit of resistance, and it has the units of ohms. If I put a potential difference delta V across a resistor R, the current that flows is given by this expression right here. It's just equal to delta V over delta R. And that makes sense. If I put a bigger potential difference across it, I'm basically pushing harder on the charges. I expect to have more charges moving. And it kind of makes sense to define resistance so that if the resistance goes down, the current is going to go up. And so we have this basic relationship here. This is known as Ohm's law, and that specifies the current in a resistor. Now the resistance depends upon two things. One is the resistivity, which is a material property. Good conductors, low resistivity. Bad conductors, high resistivity. And the resistance of resistors depends upon the resistivity, but also the length and the cross-section area. And we'll use this in a couple of different ways. And the value of the resistance is equal to rho times L divided by A. So one material variable and two geometric variables. And if you look at the rate of power dissipation in a resistor, there's three different ways we can write it. So I have energy being dissipated as thermal energy in a resistor, as we talked about on the previous slide, and the rate of energy dissipation, a power, and remember a power is a watt, and a watt, 1 watt is equal to 1 joule per second. We can calculate it as just equal to the current that flows. times the voltage, or the square of the current times the resistance, or the square of the voltage divided by the resistance. And all three of those relationships are useful in different circumstances. And it depends. Do I know the current and the voltage? Use this one. Do I know the current and the resistance? Use this one. Do I know the voltage and the resistance? Use this one. Okay? So we'll use all three of those. And those are all the relationships that we need to think about in chapter 22. Now, I want to return to this idea about the potential and the motion of charges. Okay? We're going to model a battery or any source of EMF as it's increasing the potential energy of the charges, and then they subsequently flow downhill through this external circuit. I think of this like a ski area, okay? You take, the skiers are positive charges, you raise them to a higher potential energy, so they're at the top of the mountain, and then they basically ski downhill. They end up at the bottom of the chairlift, and the chairlift increases their potential energy, and then they go downhill again. That's basically what happens in a circuit. You take the charges, raise them to a higher potential, let them roll downhill, whee, and then they end up back down here, and you send them around for another time. And as we mentioned, we define current as the charge that flows. And you can imagine looking at a wire, and you're just going to take one point in the wire and measure how much charge goes past that point in a time interval delta t, and the current is just equal to the charge that flows past that point divided by the time. And the unit is a coulomb per second, which is also expressed as an amp. Now let's take a look at the type of problem we're going to consider. So if we look at the filament in a 100-watt light bulb, it's 28 centimeters long. And if you connect it to a 120-volt supply, and we've assumed it's DC, in fact it's AC, but don't worry about that. That's a point we'll come back and talk about later, the difference between AC and DC. We're going to consider what is the force on a free electron in the filament, because we know inside the filament it's actually electrons that are moving. So I'm going to draw my filament like this. It's just a length of wire, and the filament in an incandescent light bulb is basically just a length of wire, and it's 28 centimeters long, okay? So 0.28 meters. And I put a potential difference between the ends, okay? I put a potential difference. There's a difference in potential between the ends of 120 volts, okay? And then let's go ahead and let this end be the positive end. Then there's an electric field that points from the positive to the negative. There's an electric field inside the wire. That electric field is going to exert a force on the charges. And remember, the force on charges is just equal to Q times E. And I can calculate the electric field because I know I have a 120 volt potential difference across a distance of 0.28 meters. And you know that the difference, you know that the electric field is just equal to the difference in potential divided by a distance. So you can calculate the electric field, and you can use that to calculate the force, and we will do that in class. Now, our basic circuit, and we saw that in that introductory slide, looks like this. I take the charges, I raise them uphill inside the battery, and then I just let them flow downhill through a resistor. And in this case, I'm just drawing it as a light bulb. A light bulb is basically a resistor, but we could also have a resistor, and we can model various things that way. And the current that flows is delta V over R. Now let's consider a basic circuit that is just a battery connected to a wire, and the wire has a certain resistance. And so the charges get raised uphill in the battery, and then they flow downhill through the wire. Well, let's look at that. And the question we might ask is, what determines the current? And there's a couple of things. One is the potential difference, and I can change the potential difference by just adding more batteries. And if I have more batteries, I have a higher potential difference. Higher potential difference just means more current, because we know that the current is equal to delta V divided by R. The other thing I can do to change the current is to change the resistance. And to change the resistance, I can, one, change the dimensions of the wire, or two, I can change the material of the wire, because we know the resistance is equal to rho times L over A. And we will look at examples of both of these types of situations. And as a quick reminder, the resistance depends upon geometric variables, the length and the cross-section area of a conductor, and the resistivity, and that depends upon the material, and that's our basic relationship. So let's look at some practical problems we're going to consider in class. And the first one deals with this thing called the SciFi Tube. And the SciFi Tube, if you hold both ends, it passes a current through your body, and it detects that current is being passed. And as a consequence, it makes it go wah, 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 makes sound and light. We'll see that tomorrow. I'm passing a current through a person's body. That sounds possibly dangerous, but let's look at how much current it passes through a person's body. Well, the potential difference between the different ends of the tube is equal to 1.5 volts. The hand-to-hand resistance, so the resistance from this point on a person's body to this point, a typical value is 50 kiloohms. And we can calculate how much current is going to be passed, and in fact, it's going to be so small, you're not even able to feel it. But if you have a bigger potential than 1.5 volts, it could be big enough to feel, and it could be big enough to actually be scary. And I know we've talked about this previously, about like, is high voltage dangerous? And it turns out it's the thing that is really dangerous, the thing that determines whether or not electricity is going to hurt you is not the voltage, it's the current. But the current is equal to delta V divided by R. So if you have low voltage, there's no way to get high enough current to damage you. But you can have high voltage if you also have high resistance, and that can keep the current low. So safety is a matter of voltage, but it is also a matter of resistance. And in class, we're going to consider this case. We're going to imagine a worker connecting one hand to a 480 volt wire, and the other hand is connected to a metal pipe, which is grounded. There's a potential difference between the two of 480 volts. And so there's a potential difference between the two sides of the person's body of 480 volts. We can model this circuit like a battery with 480 volts connected to a resistor, and that's the symbol we use for resistors. And the resistance is just the person's body, and we can calculate how much current we get by saying the current is equal to delta V divided by R. And we will do that for the two cases. First, assuming that 20 kiloohm hand-to-hand resistance, and then second, assuming a resistance of 500 kiloohms. And you get very, very different results and very different levels of safety. Now, let's talk about energy and power, and we showed relationships for this. The power dissipated in a resistor. We have three different relationships for it, and which one you use depends upon the particular circumstance that you're considering. And let's take a look at an energy and power problem. This is one that has to do with an electric blanket. And the way you make your electric blanket nice and toasty is there's a wire inside there that kind of like loops back and forth, and you just pass a current through it. And the wire acts like a resistor, so it dissipates potential energy as thermal energy, i.e. warms up the blanket. And for a specific blanket that I have, the power supply that runs it is 18 volts, and I want that to be a low voltage. I don't want it to be 1,000 volts because that would be a very scary blanket. So it's a low voltage, and the power that it dissipates is 82 watts. And the question that we'll solve is, given that, what is the resistance of the wire that runs through the blanket? Well, how do we solve that? Well, we say we're going to model this like a basic circuit. I've got a power supply, and that's our symbol for a power supply. And I've got a resistor, and that's our symbol for resistance. I've got a certain delta V, which we know is 18 volts. I've got a certain resistance that I'm trying to figure out. So I know 18 volts. I know the resistance. That potential difference in that resistance will lead to a certain current. I don't know the current either. But we do know the power, and we know that the power in a resistor, oops, I drew an R, let's do a P. Power is equal to I times delta V, or it's equal to I squared times R, or it's equal to delta V squared divided by R. Which one do we want to use? Well, I know the power, I know the voltage, and I'm looking for the resistance. And so it sounds like that's the correct one to use, because besides that, I could use this first one. I know the power, I know the voltage, I could find the current, but I don't want the current, I want the resistance. Or if I use the second relationship, I don't know the current or the resistance. That one is not actionable. So the one I want to look at is this one right here. And that's a problem we'll solve in class. And this is another problem we'll look at, and this is one where we use the basic circuit model, except the resistor isn't like a wire and electric blanket. It's a blood vessel. And it turns out that there are certain medical conditions that you can monitor by looking at the resistivity of blood. So we say, okay, let's take a power supply and hook it up to a segment of a person's artery. And I can pass a current through it, measure the potential difference, and therefore determine the resistance, and then I can determine the resistivity of the blood. And if the resistivity is outside a certain range, that's time to sound the alarm and kind of like see what is going on with this person. Okay, so we take a segment of the blood vessel, okay? We attach electrodes into a 1.5 millimeter diameter vein at 2.5 centimeters apart. And the question is, what is the resistivity if a 9-volt potential difference causes a 230 microamp current through the blood in the vein? So we consider the case right here. We've got a length of the conductor, which is 5 centimeters long, 0.050 meters. I know that I can compute the cross-section area as well because I know that this thing is 1.5 millimeters in diameter. I can use that to find the area. I know the length. I know the area. And our equation for resistance is that the resistance is equal to rho, the resistivity, times L divided by A. I'm looking for the resistivity. I know the length, and I know the area. If I could find the resistance, I could determine the resistivity. And I can find the resistance because I know the potential difference and I know the current. And so I can use my basic relationship for voltage, current, and resistance, which looks like this. I is equal to delta V divided by R. I know the current. I know the potential difference. I can find the resistance. Having found the resistance, I plug it in here. I know the length. I know the area. I can find resistivity. And that is a problem that we will solve in class. Now here's another problem that we'll look at. So a power line runs at 7200 volts. It's 8 kilometers long and it carries a current of 30 amps, has this resistance, and a bird is perched on the wire. Now the power line runs from the power company to your house, okay? And so there's going to be current going through this wire. There's going to be a difference in potential between the start of the wire and where it reaches your neighborhood, okay? And we know what the resistance is between those 2 points. And so because there's a current flowing through the wire, and because the wire has a certain resistance, there's going to be a potential difference between the two ends of the wire. And since there's a potential difference between the two ends of the wire, there's going to be an electric field in the wire. The electric field is equal to delta V over delta D. And since there's an electric field in the wire, there will be a potential difference between the bird's feet. And the potential difference between the bird's feet is just going to be equal to the electric field times the distance between the bird's feet. So a rearrangement of the previous relationship, but two different things for delta D. First, I'm going to say, let's calculate the potential difference across the whole wire. And so I'm just going to use the length of the whole wire and the potential difference across the whole wire, and then I'll use it again, and I'm going to use delta V to be the potential difference between the bird's feet, and this distance is the distance between the bird's feet. And this is something that we'll talk about in class as well. Now, resistivity is a material property, and we have some different values here for different types of wire. And you put a filament inside a light bulb, pass a current through it, calculate the resistance this way. We will have a chance to do some calculations with that. Now let's take a look at a sample problem. So here's an incandescent light bulb. And an incandescent light bulb has a filament inside it, and that's just a length of wire that is connected to a source of potential difference. And you can see there's two really good conductors here. And they're connected to 0 and 120 volts, respectively. So there's a potential difference of 120 volts across that length of wire. And the way you specify the power of a light bulb is you specify the properties of the filament. And when you specify the properties of the filament, you're specifying the resistance. So if I want a power of 40 watts at 120 volts, I do that by specifying the resistance of the filament. And we can calculate for a power of 120 watts, for a power of 40 watts at a voltage of 120 volts, we can calculate what resistance is necessary. And the way we establish that resistance is by determining the diameter of the wire, the material of the wire, and the length of the wire. And all incandescent bulbs these days have tungsten filaments at the operating temperature of the bulb. This is the resistivity of the tungsten, and the resistance is given in terms of the resistivity and the length and the area, as we know. So if we know the resistivity and we know the area, when we can calculate that from the diameter, we can work out what the length has to be. And we'll do that in class, and I'll give you a preview. It's longer than you think. It's very, very long. And so the question is titled, how do they fit it in there? And that is actually a good question, and we will talk about that. Now, we're also going to look at electric fish this week, which I'm pretty excited about. And they have these cells called electrocytes. We'll talk about how they work. And an electric eel can make a really, really, really large voltage because each one of those electrocytes can make a voltage of 150 millivolts. But it stacks them in series, okay? And it can have up to 6,000 stacked in series. What that means is you get 150 millivolts from the first one, and the second one you get another 150, and the third one you get another 150, and you just keep stacking them. And as a consequence, you get a voltage that's the total of the voltage of 6,000 of them connected together, and so the electric eel can pack quite a punch, as we will see. Now, another thing that can be connected in series is things that dissipate energy, like the LED mini lights that you've seen. And if you have a bunch of lights like this, okay, a whole bunch of lights in a string, they're actually connected in series. And typical numbers would be 50 LEDs connected in series and connected to a 120 volt outlet. We can work out the voltage across each bulb. It's basically shared among them. And we can also work out the total power. And those are a couple things we'll do in class. Now, finally, we're going to start talking about properties of circuits. And the first thing we're going to look at is conservation of current. Current is the flow of charge. Charge is conserved. So if I have a current that comes to a junction in a circuit and it splits one way and another, the output current has to be equal to the input current, because current can't be created or destroyed. The sum of the current into a junction has to equal the current out of a junction. And the first example we'll look at looks like this. So I've got 7 amps here, I've got 5 amps here, and I want to know what currents C and B are, okay? And basically what you would do is this. 7 amps comes into the junction here. 5 amps goes out. How much has to go this way? Well, the current coming into the junction is 7 amps. I got 5 amps going this way. How much has to go this way is 2 amps. So that 7 amps comes into the junction and 7 amps goes out of the junction, 2 amps that way, 5 amps this way, a total of 7. And then if I look at the other junction, 2 amps comes in as current IC. This is 2 amps. 3 amps comes in here. How much has to go out here? There has to be 5 amps that goes out here because, again, the current into and out of the junction has to be equal. And that's a principle of circuits we use repeatedly. Now we're going to take a look at series circuits. So suppose I have one bulb hooked up to a battery, and then in a second trial I take 2 bulbs and hook them up to the same battery. And the question is, how will the brightness vary? Well, for the brightness we're going to use is basically a proxy for current. Suppose I have a 3-volt battery here. Okay, 3-volt battery, this light bulb gets the entire 3 volts. But if I look at trial 2, I have 2 bulbs hooked in series. Got a 3-volt battery. Each one of these bulbs is only going to see 1.5 volts across it. And since the current in the battery is equal to delta V divided by R, if the bulbs have less voltage across them, they will have less current through them, because we assume the resistance is a property of the bulb, and that is something that is fixed. And so I'm going to predict in the second trial that the bulbs will be dimmer, and in fact that is what you will see if you were to set this up and do this. Okay? And then we're going to look at more complicated circuits, and we're going to do this. In this circuit, we're going to rank the bulbs according to their brightness. Now, 2 things are at work here. One, I want to look at potential differences at different parts of the circuit. But the other thing I can consider is current. And think about this. Any current that goes through bulb A, ultimately has to go through bulb D, because any current that comes out of the battery has to come back into the battery. So the current in bulb A and the current in bulb D should in fact be the same. So I'm going to predict their brightnesses are the same. But let's look at bulbs B and C. Current comes out of bulb A and it splits. Some of it goes through bulb B, some of it goes through bulb C. And so the current in bulb B and C will be less than in bulb A and in bulb D. So I'm going to expect them to be dimmer. But how about their brightness relative to each other? Well, they're connected together here, and they're connected together here. And so the potential difference across bulb B is going to be the same as the potential difference across bulb C. And since the current in the bulbs is delta V over R, same potential difference across them is going to give the same current. So I'm predicting bulbs B and bulb C will have the same brightness. And here's a summary of those laws for circuits. They're called Kirchhoffs Laws. Don't worry too much about those details. We'll play with them in practice and you will see how they work. One thing we'll consider when we're doing circuits is the wires that connect different things together are ideal, i.e. I don't have any potential difference across a wire. And that's a pretty good approximation for the wires that we use in lab and the ones that we use in problems. And then we're going to finish the week by doing some complex circuit puzzles. And we're going to start using symbols for circuit elements. So rather than drawing a picture that looks like a wire and a light bulb, we'll start to use symbols. This is my symbol for a potential difference. This is my symbol for a light bulb, and a light bulb is just a resistor. We have to rank those bulbs according to their brightness. I'm going to give you a quick hint. What can you say about the current through bulb A and B? That'll allow us to say something there. And then let's think about the potential difference across bulb A and B versus the potential difference across bulb C. That's how we'll approach that problem. And then we're going to look at another one, kind of like bulb brighter or dimmer, and you're going to say, like, Brian, why are you so obsessed with the brightness of light bulbs? I'm not. This is kind of a really good way to have us think about circuits, okay? And think about circuit properties. And I'm going to say this. Here's a hint. Bulb D, surprisingly, is going to be the brightest. And you might say it's at the end of the line. Isn't all the energy used up by the time you get there? No, it can't be. There has to be enough energy to push all that current through bulb D. And any current that goes out of the battery has to come back to the battery. So any current that comes out here has to come back here. Bulb D gets all the current, and then when it gets here, it's going to split. Some of it goes through A and B, some of it goes through C. So those bulbs will be dimmer, and the rest we will talk about in class. And then we're going to take a look at this one and starting putting in some numbers. And so we're going to use that equation that I is equal to delta V over R and apply it to a specific case. These are the types of problems that we're going to be considering in chapter 23. So by the end of the week, we're going to be jumping into material, which is in chapter 23. And we'll also talk about how to reduce circuits. If you have a complex circuits with multiple resistors, I can take those 3 resistors and turn them into 1. So if I had a 1 ohm resistor and another 1 ohm resistor and a third 1 ohm resistor all connected in series, I can treat it as a single resistor with a resistance of 3 ohms. We can do something similar for bulbs in parallel. And in this case, if I have a 3 ohm resistor and a 3 ohm resistor and a 3 ohm resistor all connected in parallel, the resistance is equal to 1 over 3 plus 1 over 3 plus 1 over 3. I take 1 over the whole thing. I would end up with a resistance of 1 ohm. And we'll look at some shortcuts for doing that. And finally, we'll finish the week with a complex circuit puzzle. And I don't want to spoil the surprise, but this is one we're going to finish with, and that is really going to lead us into the material we're dealing with in Chapter 23. So there's a quick overview of the concepts and the types of problems we're going to be looking at this week. This is Circuits Part 1. Thanks much.